So we're going to do an example. We have a little hidden Markov model that can generate basically sequences of characters. And it can only generate one of three characters, a M, a H, or a O. Okay. So we're not doing parts of speech tagging anymore. For this hidden Markov model, we're just generating stuff that are combinations of M, H, and O coming out of this model. Okay. And the hidden Markov model has a start state, an end state, and then two inner states, two emitting states. I call the one state C and the other state V. And C is kind of like consonants, and V is kind of like vowels, but not exactly. For example, if I'm in the consonant state, then M, which is the consonant, gets output more than H and O, but H and O also sometimes pops out. Okay? If I'm in a vowel state, then O pops out most of the time, but sometimes a H, which can kind of sound vowelish sometimes, or an M also pops out. So this might be, let's say we've got a 9-month-old child. The child has learned three little sounds, m, o, and h, okay? And now we can have this little model generate sounds that sound like a child, okay? And it can generate things like momo, or ho-ho, or ho, or mo. For this example, I give you the probabilities for everything. I tell you how to transition from one state to another, and I tell you how to output characters when I'm in a particular state. The question I ask is, I've observed a sequence, and the sequence I've observed is m or h. And I ask, should I label this as consonant, vowel, consonant, or vowel, vowel, consonant, or consonant, consonant, consonant? What is the optimal state sequence through this hidden Markov model? What is the underlying thing that led to this observation? Let's just draw the hidden Markov model. So we've got a start of sequence state. Then we've got two inner states, the C state and the vowel state. I'll talk about these things as consonants and vowels, but just remember they're just a name for states. They're not actually consonants and vowels, because otherwise we would just know M is a consonant and O is a vowel. I'm just using this as an analogy to label the states. Okay, so C and V are just names of these states. And then we've got the final state, which is the terminating state, called end of sequence. Now I'm drawing the state diagram here. What's the probability of going from the start of sequence to vowel? The probability of going from state to vowel is 0. That's right. Okay. From start to vowel is 0. Okay. So I'm not even going to draw in that arrow because that never happens. So actually, here's a question. Where do we go to when we start a sentence? What do we always start a sentence with, or always start a sequence with, according to this? C. Yes, we always started with a consonant. We always started with a C. So we always move with probability 1 to that state. Okay, and the other probabilities are 0. Okay, let's sit in that state. If I'm in a consonant, what's the probability of staying in a consonant? 0.2. Like I started at the consonant, I'm moving. Next state is also consonant, then it's 0.2. Okay, and you can actually fill in all of these probabilities. The probability of being in a vowel, if I was in a vowel before, is 0.1. The transition probability of going from a consonant to a vowel is 0.4, and you can scribble that. You can scribble all of these things in if you want to. Let's just do one more. So ending. When I was in a vowel before, I'm ending, that's 0.2, so that would be a 0.2. Okay, we haven't looked at the emissions yet. Let's do that now. So let's say I'm generating from this model, so I do a consonant and I output something, and then I move to vowel and I output something. Then if I'm in the vowel state, then my emissions is I can output an M, I can output an H, or I can output an O. And the probability if I'm in a vowel of outputting an M is what? I'm in a vowel state. What's the probability of outputting an M? 0.1. That's right. 0.1. So the 0.1, I'm in the vowel state. I'm looking at this row. This is a row that sums to 1. That's the output distribution for my vowel state. 0.1 for M, 0.3 for H, and 0.6 for vowel. Okay. And then for the consonant state, you have, you can read it off there. You also have the probabilities for M, H, or O. Okay, awesome sauce. Okay. The problem is that I'm trying you to solve is I've observed MH, MOH, and I ask, how does this sequence come about by moving through this state diagram? What do you think is the best path through just staring at it? What do you think is the path with the highest probability? CVC, very often syllables are CVC. Okay, so it's a good guess, but you need to do it properly, right? Okay, we will figure out what the answer is. The one interesting thing that you can do is you can just ask a M, just on its own. It can come from C or V, right? And the M on its own comes from what? Well, 0.6 is higher than 0.1. So I could have just said, okay, well, let me just guess that this is C. And then for O, I could have said like, you know, this 0.6 is higher than 0.2, so I'll guess that's a V. And then for H, the higher one is V, so I could have guessed V as well. Okay? But what's the problem with that? Okay, apart from that 0.6 and 1 together doesn't make a valid probability. The other thing that this ignored is that transitioning from consonants to vowels might have very different probabilities than some of the other transitions here. So for example, a VV transition, let's just look at this, a VV transition actually has a very low number of 0.1. And this greedy guess that I made ignored that completely. So let's do the Viterbi algorithm to figure out how to get something that's better than my bad guess. What we're going to do is we're systematically going to try and fill in this table. And this table is really just my delta T, J. Okay? So T goes from, T is equal to, it can be 0, 1, 2, 3, or 4. Okay? And then the state that I can be in those different time steps, state is either 0, 1, 2, or 3, where state 1 is a consonant and state 2 is a vowel. Okay? And we're just going to fill in this monstrosity of a table. Okay? And then in the end, we will see that Viterbi actually solves all our problems in life. Okay? And let's just start off. I actually wrote the Viterbi algorithm just there at the top there. Okay? So if you just look at the Viterbi algorithm there, we're going to follow those steps and we're just going to fill it in. Okay, and then I'll also just put up the matrices for the specific HMM so that we can easily look it up. Okay, so let's start with the easy part. Where do we start? We always start in the start of sequence state. We always start there with probability 1. Okay, and that's just the way I set things up. So there's a little mistake here. That should be end of sequence. Yes, thank you. So let's just step through the Viterbi algorithm. But the first thing is to initialize things, and that's when you're moving from the start state into the first state. Okay, and that's that initialization. So we're in time step 1, and we're looking at these deltas for these different time steps. Okay, so let's just do t is equal to 1, t is equal to 1, and the equation for the first time step 1, for the different stage j, is just equal to the probability of outputting the first thing, and actually I'll write all of this in capital letters because it's discrete. Okay, the probability of outputting the first thing given that I'm in this specific state at time step 1, times the transition probability of going from my start state into the state j. Okay, the probability or the delta at time step 1 for being in a constant is equal to P of, okay, now let's just write this out. The first observation given the state constant times the probability of transitioning from my start symbol into a constant. Okay, what's the first observation? What's the first thing that I observed? The first thing we observed is an M. Okay, and given that I'm in a constant state, this is my one option that I'm considering, and then I'm moving from the start of sequence into constant. Okay, cool. And you can actually tell me what the values are on the board there. What's the probability of generating an M when I'm in a constant? 0.6. And then what is the probability of transitioning into a constant from the start sequence? 1. 1 is correct. Okay, so that's 0.6. So what we do is, at time step 1, when we've generated M, our one option is to be in state C, and the delta term for that case is 0.6. Okay, you with me? And you can actually put the backtrace in already. So next up, we're going to consider this option of being in a val in time step 1. So we're at time step 1, and the option is val, okay? And we can simplify this. So it's the probability of the observation at time step 1 is what? M, okay? Given that I'm in a val, times the probability of going from the start to a val, okay? What is the probability of M given that I'm in a val? 0.1 is correct. 0.1 times, okay? And then the transition probability from the start of sequence to a val, what's that? 0. Perfect. So we've got a 0. And we can fill in a 0 in that point. Super boring, okay? We'll look at a slightly more interesting one now. So let's look at this step here. We look at time step 2, and we're considering being in a consonant in time step 2. Now you need to go and look up, because now the Viterbi process changes a little bit, right? Because now we're in the recursive part, where we're using previous deltas in order to consider the current delta, okay? So the equation there is at time step 2 for state J is the max over all my previous, over all the states, times the probability of generating the current observation, given that at time step 2 I'm in state J, times the transition from the previous state into the current state. Aj, and then delta 1 of being in state I. Let's just stare at that a second. So what we're doing is we're considering at time step T whether we're in some current state. And what we're doing is we're considering different options of coming from a previous state. And what we're saying is, okay, well, I'm in the state that I'm looking at now, state J. I could have come from state 1, or I could have come from state 2. Okay? If I came from state 1, I need to transition from state 1 to state 2. And I have my delta from stage 1. Or I can come from state 2, which means I transition from state 2 into J, and then I need to pay the delta. Or I get the credit for the delta where I was before. We're considering this thing here. So we're considering, when we've observed O, whether we're in the consonant state. At time step 2, we're asking, are we in the consonant state? And we're going to take the max over two things, okay? The one option is that we came from state 1. State 1 is the consonant state, okay? And then the other one is that we came from state 2, which is the vowel state. What are we observing at the moment? O, that's right. Option 1, when I is equal to 1, we've got the P of O, given that I'm currently in the consonant state, times the probability. So the first option is that I came from a consonant. So times the transition from a consonant into a consonant. I'll draw this out in a second. Times that I came from consonant. Okay, that's option 1. Option 2 is that I'm currently outputting an O, given that I'm in the consonant state, times the transition of coming from a vowel, going into a consonant, and then I've come from a vowel in the previous at the previous time step. I know the math looks tricky, and I'll show it on the diagram in a second, and then it will be super clear. Okay, so we've got the max of two things. What is P of O given C? 0.2 is right. What's the probability of going from a consonant to a consonant? 0.2 as well. Are you sure? Yes, you're right. Times, okay, and then the delta 1C. Now delta 1C is this value here that we calculated before. My second option is 0.2, generating an O given that I'm a consonant, times the probability of going from a vowel to a consonant. What's that? 0.7 is right. 0.7 times the delta of coming from a vowel in time step 1. What's that? 0 is right. Okay, so we end up with one option. It's an easy one. That is the option that we end up with, and that gives us a value of, you can go and type this into some calculator, 0.024. Okay. this option here, we're trying to fill in this cell. And that first option is basically saying, what if I came from here? This second option here, that's the option of being in a val in the previous time step. So that's the question that I come from there. Okay, and those are your only two options. And it turns out, if there's a 0, then that's probably quite a bad option. So I'm probably not going to come from this direction. So let's just remove that and make it a little dashed line. Okay, because we didn't end up coming from there. And then you fill in this value 0.024 in this cell. Does this make sense? You can, I don't know, should I do more? Can we just stop there? Okay. You actually, what ends up happening is you fill in the table right in this similar way by every time. So if I'm filling in this cell, I basically have two options. I can come from here or from here. Okay. In this cell, which way will I come from? You can already see what the answer will be. Do I come from consonant or from vowel? Who votes for consonant? Okay, cool. No one votes for vowel. Okay. Why? Because coming from a vowel is a 0 probability. So that's right. You're coming from there, and you can go and work it out. It's actually relatively simple. So this cell, to work it out, I take the probability of generating an O, given that I'm in a V. What's that? 0.6. 0.6. Okay. Times the probability of transitioning from a consonant to a vowel. What's that? 0.4 is right. Times the delta that I earned in the previous time step, which is 0.6, and that gives you 0.144, and this is for delta 2 being in V. Okay, and you can fill up the whole table in this way. When you're moving into this cell, you don't have any output, so you're only considering this times the transition of a consonant into an end state. And for this option from here to here, you're just considering this delta times the transition probability from a vowel into the end state. Now this is important, like what the fudge was our goal to start out with, right? We had an input sequence, x1 to 3, which was M, O, and H, okay? And then we ended up with this table, okay? And so what is the state sequence? Now all we have to do is we need to backtrack. We know we ended off with this probability, which is the probability of following this optimal state sequence. And this is always the probability of following the best state sequence, is always that. And if we've kept track of how we got here, then we can just backtrack. So we know we end in state, end of sequence. Okay, that one is easy. Okay, and then what we know is before that we were in, what's this? Consonant or vowel? Consonant. Before that we were in this. What's that? Vowel, consonant, and then start of sequence. So we can backtrack. We know that at time step 3 we were in consonant. We know that at time step 2 we were in vowel, and we know that we were in time step 1 in consonant, and we know and this is the dumb one, we always know that we start the sequence at the start. Epic. Okay, and so if I now give you a hidden Markov model, and I give you its parameters, and I give you an input sequence, and I ask you, what is the optimal state sequence through this hidden Markov model? You can do it. Okay, this is also super important. With Viterbi, there's no approximations. You're not making any approximations. You're guaranteed to get the best path through your state machine. Okay, no approximations. Okay, so that's very, very important. This is the globally optimal path through the state machine. Yeah, a little bit magic, right? If you think about it. So I didn't have to contemplate all the paths, and I still got the best overall path.